good morning or good day. How are you, my dear students? I gave you additional problems in chapter 5. Before we leave the chapter, we need to understand additional concepts of forces, now including tensions, and what we call the free body diagram. My dear students, it has been our practice in solving the problems that we need to have a sketch, a drawing, and the importance of having such as a requirement in solving the problems will be realized in problems 90, 91, 92, 94. Because without that sketch or diagram, it would be difficult for anyone to make immediate and direct solution of the problem without basis, and such basis is the diagram. Here we will have what we call the free body diagram. Okay, I have with me the book again. Then I have here problem. Let's start problem number 90. I will read the problem. A crate of mass 2,000 kilograms is hanging from a crane at the end of a cable 12 meters long. So there is a big box, the crate, okay, being hung at the end of the crane, tied with a cable. Okay, it's a cable wire actually. Length given. If we attach a horizontal rope to this crate and gradually apply a pull, pull, because force is either a push or a pull. So apply a pull of 1,800 newtons. Okay, 1,800 newtons. What angle will the cable finally make with the vertical? Meaning to say, with that pull or force of 1,800 newtons, what is that angle it could make? Here we need a diagram. Okay, I'm going to get my pen. Okay. Let us have here the cable. Okay. It's not a straight line. Okay. Then there is the crate here. There is the crate. This cable has a length. It has a length of, let me check the length of the cable, 12 meters. So 12 meters. the length of the cable is 12 meters. This is the crate. This is the crate. And this is the cable, 12 meters long. And a force is applied, attached here, there is a rope. A rope will be attached here. Okay. Okay. And a force is applied. And the force here, F, the pulling force, pulling, F sub P, pulling force, equals 1,800 newtons. Okay, that's the pulling force. Then, this is the cable attached to a crane. There is the crane here. You have seen a crane. Okay, so there is a crane. Just imagine there is a crane. Our diagram will focus on the crate and the cable because we have here forces acting on the crate. There's a force being acted on by the cable, and that force, we call that force the tension. There is this tension, okay? And there is this force, F. F sub P. Okay. And so, when this is being acted on by the force of 1,800 newtons, then the situation would be like this. Okay? The situation would be like this. This will be, the cable will be like this, the crate will be like this. This is now the crate. Okay? You have here the force, F sub P, and you have here the tension. You have the tension here, tension T, and you have here the angle. You have the angle theta. That's the angle. What is the angle theta equal to? With the force F sub P equals 1,800 newtons. Let us have the other information here. Then the crate has a weight, a mass of 2,000 kilograms. So, in other words, this one has a weight. The weight of the crate, which is equal to mg, where m is the mass. M is the mass given 2,000 kilograms. G, a constant value, acceleration due to gravity, 9.8 meters per second squared. In the book is using 9.81 meters per second squared because the average value of all the values of G gathered all over the planet based on their recent measurement by the book is equal to 9.807. G, okay, G equals 9.807 meters per second squared. That is why the book is using 9.81 meters per second squared. Remember in our previous discussion that the G from one place to another place is different. And that difference, okay, is dependent on the location. From the North Pole to the equator, there is a change there of what we call acceleration due to gravity. Above the equator and below the equator, different G's. You can access that in the internet. In the case of Silliman campus, the acceleration due to gravity is 9.782. Acceleration due to gravity is G in Silliman University, 9.782 meters per second squared. And on the average, that is the acceleration due to gravity in Dumaguete. There's a difference in the last two digits. If you are going to round this off, this will be equal to 9.8 meters per second squared. Okay? Something like that. With this value or this value, it does not matter. What matters here is the application of the concept, the principle. Okay? That is what matters most. Okay, you can use 9.8, you can use 9.81. Okay? Okay. Now, you are asked, what angle? Now, let us have other information here. I'm looking at the other information. Okay? So, these are all. How to solve this problem? If we are going to analyze this particular problem, we need to understand that forces involved in this problem have components. Components along the x-axis and components along the y-axis. Now, what is the x and the y-axis? We have here this is the y-axis, positive y. This is the x-axis, the positive x. This is the negative y. And this is the negative x. I discussed this one with you in our previous discussions. I am going to repeat this one. You look at the video discussions I had with you. Okay? I already discussed this one. I will repeat. You will have here first quadrant, second quadrant, third quadrant, and the fourth quadrant. So there are 4 quadrants. On the first quadrant, the x-coordinate, you have here, x-coordinate is positive x, y-coordinate is positive y. Second quadrant, negative x, positive y. What is the third quadrant? I will answer my question. Negative x, negative y. What is the fourth quadrant? Positive x and negative y. These are the respective corresponding signs of x and y coordinates on the 4 quadrants. Okay. Now, for the force F sub P, the pulling force, the force here F sub P. This is our F sub P along the positive x-axis. Then the tension here, our tension is here. On the second quadrant, this is our tension. Our tension located on the second quadrant. And therefore, tension has two components, x component and y component. You have to remember that any vector quantity has components. Force, the pulling force is a vector quantity. Or force in general is a vector quantity. And therefore, it has two components in two-dimensional system. Okay? But in three-dimensional, you have the third component, the z component. And in vector analysis, we have unit vectors we call I, J, K. You can find this one in chapter 2. I, J, K. Where I is a unit vector along the x-axis. J is a unit vector along the y-axis, and K is a unit vector along the z-axis. So you have unit vectors, I, we call this one I hat, this unit vector I hat, we read this one as I hat. You have J hat, it's a hat. It's a hat. Then K hat. K hat, not the hat there as K hat. K hat. K hat. So this is unit vectors I, J, K. Okay. Now we are not using here forces with, okay, strictly applications of unit vectors ij in two dimensions. Of course, our answer, if you want to be a little bit technical, must carry these unit vectors ijk. But I know, my dear students, you need more readings on this one. Okay? I did not discuss this one in detail in chapter 2 because we might be unable to reach several chapters ahead of us, and we still have some experiments to come. Okay? So here. So, this one is on the third quadrant, and therefore the tension has components along the negative x and along the positive y. Okay? Negative x, positive y. Okay. Now there is the third force. The force coming from the weight, because this one has a weight, W. By the way, I started the weight here intrinsically, okay, inherently is at the center of the body, assuming that this crate is a perfect square or rectangle. For any body that has a geometrically, okay, shaped or formed rectangle, triangle, these are geometrical, in geometry, it's a perfect one. Okay? It's a regular body. Unlike this one, unlike this. This is irregular. This is an irregular body. Or this one. This is an irregular body. This one is a regular body. And for any regular body, the weight is assumed to be concentrated at the center of the body. How about my body? How about your body? Is it regular? In geometry, it is irregular. And so, being irregular, where is the weight of your body concentrated? Assumed to be concentrated. Because it is an irregular body. My body is irregular. In geometry, you cannot find a name of my body. Also, your body, in geometry, what particular shape your body has? No particular shape. And so, we label that, we categorize that as irregular body. Of course, in the physical world, there are only two categories of bodies, regular and irregular. Okay. Now, so you have that. Irregular. This one is regular, assumed to be at the center. In the case of this one, I will get a meter stick here. This meter stick is a regular body. What kind of shape or form in geometry? What's the form? What's the shape? That's my question. What's your answer? I will answer my question. This body has a rectangular shape. Regular. And being regular, the weight of this body is concentrated at the center. Where is the center of this meter stick? Where's the center? Where's the center of the meter stick? The center is at 50 centimeters because the length of the meter stick is 100 centimeters. And the center of the meter stick is at 50. So, being regular, all the weight of the meter stick is at the center. So, 50. I have here 50. Okay. So, 50, you see, it is balanced. Balance. Why balance? Because all the weight of this meter stick is concentrated at the center. We call this one the center of gravity. Center of gravity. Center of gravity. At 50. Here, 50. Balance at the center of gravity. True to any regular body like the meter stick. But for an irregular body, let me check. Where is the irregular body? I will look at the irregular body. Where are you? I'm looking for an irregular body here. I don't have the irregular body. I don't have the irregular body. I'm looking for an irregular body. Regular body. Where are my instruments here? Okay. Irregular body. Irregular body. Irregular body. The fourth is an irregular body. What is the name in geometry? Is it rectangle, square, cylindrical? Okay. Pyramidal. What are the shapes in geometry? You know. This one has no shape name because it is an irregular body. Being an irregular body, the weight of this fork is not at the center here. The center. Center means one half. One half, one half. Let us measure. Let us measure the length of the fork. The length of the fork here is 19. Oh, 19. 19 here, 19. 19 is before 20. 19. I will have this mirror. Okay. It's 19. Now, what is 1/2 of 19? What is 1/2 of 19? Huh? What is 1/2 of 19? I will answer my question. 9.5. Okay? So 9.5. So it will be here 9.5. Oh, here. So 9.5 here. So this is 9.5. I'm going to put my finger here. My finger serves as the fulcrum. You have heard of the term fulcrum? F-U-L-C-R-U-M. Fulcrum. So this is now the fulcrum. My finger, this index finger, put here. This is 9.5. The center of the fork, 9.5. I'm going to balance. Ready? Sige. Ready? Gets it. Balance. Ready? Gets it. I'm going to release. Balance. Oh no! Oh no! Oh no! Not balance. So it's not balance here. Why? For an irregular body, the weight is no longer concentrated at the center. We have to locate that, what we call center of mass. So, to balance, you have to make some trial of an error. Balance. Oh, there. Huh? Supposed to be here. But I could not balance the fork. Why? The weight is no longer concentrated here. Why? Because this fork is irregular. Okay? This fork is irregular. Okay? Okay. So here we are. We cannot balance this one. Okay. There is a ring. Somebody is calling. You know, I'm using the cell phone as my recorder. Wait, I'm going. It stops. Let me check. It stops. Okay. So no more disturbance. Sorry for the caller, Sorry. Caller, sorry, I have a video discussion. Oh, it's balance! Balance! Why balance? Because the fulcrum, which is my index finger, this index finger, the fulcrum, where my index finger serves as the fulcrum hits the center of mass, so it's balanced. So we have what we call equilibrium. In this problem, we'll have equilibrium condition. Okay, in that problem. So, here, weight concentrated at the center, weight is a force, weight equals mg, weight is a force, so there are how many forces acting here? How many forces? How many forces? I will answer my question. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. So there are 3 forces. Okay? Okay. Let us call the weights. Let us call the weight. This is our equal to F1. This is equal to F2. And this is equal to F3. So there are 3 forces. 1, 2, 3. Now, we get the what we call equilibrium condition. That when the force of 1,800 newtons being applied on the crate when the force, the pulling force of 1,800 newtons is applied on the crate, that force can only have, okay, the production of theta, which theta will be maximum, which theta is required to have equilibrium. Because if theta is not yet the equilibrium angle, the force continues to pull this one, okay, the 1,800 newtons will continue to pull this one until it attains the required angle theta. And at that required angle theta, there is equilibrium. When we say equilibrium, the crate now will be at rest. The pulling stops there. No more moving the crate farther because the maximum angle required has attained. And at that particular angle, the problem assumes equilibrium. If that is so, then we are going to have summation of forces. This is Greek letter sigma. Sigma. For letter S in the English alphabet. In the Greek alphabet, sigma. Summation. The sum. Summation of forces here equals 0. And this is true only in equilibrium condition. When all forces acting on the body, in this case, the crate, balance each other, sum up to 0, then we have equilibrium condition. Remember that. In any equilibrium condition, in the case of forces, summation of forces equals 0. Or, technically, we say the vector sum of all forces acting on the body equals 0. The vector sum of all forces acting on the body equals 0. Because forces are vectors. So, we see the vector sum. Okay? Okay. Now, the forces here involves X and Y components. So, we have summation of the X components equals 0. Summation of the Y components equals 0. We have here a perfect equilibrium in terms of forces. In terms of torques, we sum up also the torques when we are dealing with rotation. When we are dealing with rotation. Here, no rotation. The problem is telling us horizontal pull. Horizontal pull. So, linear, no rotation. Linear motion. Linear motion executed by the crate. And that linear motion is maintained only at an angle theta. Because if you increase the angle, there will be rotation. There will be rotation. If you increase the angle is bigger than what is required, then the body will execute a rotation. The body will execute a rotation. And the cable wire now here will become the radius. The cable wire will become the radius. Okay? That's why only a certain angle, beyond that certain angle, there will be no more linear motion. Okay? There will be a manifestation of a circular motion, a rotation. But here, the problem should maintain what is required, linear. So the angle here must be very small. The angle here must be very small. What is that very small angle? We will solve that. Okay. So you have this one. Okay, you have this. And then, after having this one, we will now have this one. This. Summation of forces. Along the x, summation of x is equal to, now here, you have f sub 1x plus f sub 2x plus f sub 3x equals 0. Remember, there are three forces. F1, F1, F2, F3. And for every force, F1, F2, F3, there are two components. X component, meaning the component of the force along the x-axis, the component of the force along the y-axis in two-dimensional system. As I told you, it would be better if we solve that in three-dimensional system. However, the working principle in solving the two-dimensional system, the same principle will be applied to three-dimensional system. Only there are additional variables. Okay. Here, in other words, you will have here f1x plus f2x plus f3x equals 0. Now, f1x refers to f1 the way. Okay? If we are going to consider the angle, or the angle is measured based on the positive x-axis, then the angle of f1 will be 270 degrees. 270 degrees. This one is 270 degrees. This one is 270 degrees. 270 degrees. From here to here, 90 degrees. From here to here, 180 degrees. From here to here, 270 degrees. From here to here to here to here, until here, 360 degrees. Okay? Okay. Now relax. You can review this video. Anyway. So, in this case, you have F1 cosine 270 degrees. We use cosine for x component. Plus F sub 2. F sub 2. Components, cosine 0. Because F sub 2 has an angle 0 degree. F sub 2. The pulling force. The angle is 0 with respect to the positive x-axis. Remember that 270 degrees is measured based on the positive x-axis. Then, plus F sub 3 cosine. Okay. Our F sub 3. Now, this is our F sub 3. Okay. The angle here is theta. If the angle here is theta, I hope you can just see this one. Huh? Okay. I will have this one here. This one, I will transpose this. I will transpose this. Third quadrant. Transpose. Third quadrant. Third quadrant. Okay. This is our tension. This is our F3. Tension. Or equals F3. Okay. Tension equals F3. T equals F3. F3 equals T. The angle here is theta. Theta. The angle is theta. If this one is theta, then this one is theta. Right? That one is theta. Okay? Or what? Theta is equal to what? If this is theta, we can call this one alpha. We can call this one alpha. This is theta. Okay. This angle is equal to this angle if we assume that to have this one. Okay? They are just equal. Okay? Or, you can have, so that you will not be confused here. You can have here alpha, you can use also alpha is equal to 90 degrees plus theta. Alpha here, alpha, okay, equals 180 degrees minus theta minus 90 degrees if you want to be a little bit complicated. Or this minus theta minus 90 degrees, we can call that beta minus beta. Or another approach here is that you can focus here. Okay, you can focus here. This one, this is here cosine theta plus 90 degrees. Theta plus 90 degrees. Or, okay, to avoid this one, by the way, this is equal to 0. Another way of solving this one, because you have here, maybe not so good for you to see this one, cosine of theta plus 90 degrees. Not so good. So, we need to simplify this one. We need to simplify this one. Because you know, oh, what is that? Theta plus 90 degrees. We are referring to this angle. Okay? If you have like this, you can simplify this one. Okay? Concentrate here. Our f sub 2, oh, you cannot see this one anymore. I will be here. Okay. This is our tension. Okay? If this is theta, and therefore this one is theta, okay? They are equal, okay? We can just have this particular triangle. We can have this particular triangle. In other words, focus so that there will be no more involvement of the 90 degrees. Focus here in this triangle, a right triangle. This is a right triangle. That is a right triangle. You have here the hypotenuse. This is the hypotenuse. This is the adjacent side to the angle. This is the opposite side. So, the triangle will be like this. Okay? This will be the triangle. This one is theta. This is the hypotenuse, the tension, which is equal to F3. This is the adjacent side. This is the opposite side. And therefore, if we get the x component, this is the x component. This one is our x component. This is our x component. Okay? This one is our x component. We call this one F 3x. X component along the x-axis because this is the x-axis. And this is the y component. F3y. So, for F3x, using the right triangle, for F3x, using the right triangle, you will have here F3x, okay? Using the right triangle, you will have here F3 sine theta. Sine theta. This is the opposite side. F3x sine theta. F3y, adjacent side. Adjacent side to the angle theta. F3 cosine theta. Why cosine for this side? Cosine because we get the F3y here, which is the adjacent side to the angle theta. F3x is the side opposite to the angle theta. Opposite to the angle theta. So, sine theta. Why this one is F3x? F3x because it is a horizontal. Okay? Horizontal side of the triangle, which is the x-axis. This is the vertical side, the y-axis. So, to avoid the use of this one, I'm going to erase that. You have here F3 x component, F3x is F3 sine theta. I hope you get the explanation there. This one cosine, sine. This one is cosine because we get the angle based on the positive x-axis. This is sine, this is cosine because the angle is taken from the positive x-axis. Why sine? Because the angle here is taken from the y-axis. Remember, theta here is taken from the y-axis. This is the positive y-axis. Y-axis. Below is the negative y. This is the x-axis, positive. Theta we use sine because the angle is taken from the or based from the positive y-axis. We use sine. If the angle is based from the x-axis, we use cosine. We use cosine. So that's why cosine? Because the 270 degrees is measured from the positive x-axis or from the x-axis. Measured from the x-axis. How about cosine 0? Cosine 0, F2 is the pulling force. The angle 0 is taken from the x-axis. We use cosine because the angle is taken from the x-axis. Why sine? Because theta is taken from the y-axis. We use sine. Okay. Theta is unknown. We do not know theta. The 0 degree, we know because the pulling force is the angle. It is having the angle of 0 relative to the x-axis. The angle of the pulling force, F2 is the pulling force. The 0 angle is measured from the x-axis. 270 degrees, the angle is measured from the x-axis. 90 plus another 90, 180 plus another 90, 270. 90 degrees. From here to here, 90 degrees. From here to here, another 90. 90 plus 90, 180. Another 90, 270 degrees. That's why you have 270 degrees. The angle, we use the trigonometric function cosine because the angle is based, measured from the x-axis. We use sine if the angle is measured from the y-axis. Okay? Okay. Relax, relax. Now, so you have this one, equals 0. Okay. Why 0? Because of the assumption that there is equilibrium. Okay. At a certain angle where linear motion is maintained. This one. Linear. Pak! Stop! Because beyond that, it will be rotating. You have now a rotary motion, and therefore, you have to engage with the torque. Torque causes a body to rotate. Okay? Torque. T-O-R-Q-U-E. Torque. Torque causes a body to rotate. To avoid the torque, linear motion is maintained. Approximately maintained. I will say approximately because if we go to the very technicality of this one, even a small angle will allow us to have what we call angular motion. But there is what we call some limiting value there. In one of your experiments to come, we will have the simple harmonic motion, where we can approximate a simple harmonic motion if the angular motion is avoided. And this is now a preliminary to the simple harmonic motion. Because once we have this angle bigger, there will be angular motion. Rotary. Here, a certain. Okay, this one. Then, let us have the substitution here. Our F1 equals the weight. No problem. Weight equals M times G. M, the mass. I will look at the book. The mass. 2,000 kilograms. Mass 2,000 kilograms. G 9.81 or 9.8. Your choice is as good as mine between the two. No problem. Okay? You use this one, 9.81, or you use this one, 9.8. It's okay. Okay? It's okay. Because this is the standard. In most of the books, they are using 9.8. There is only one digit after the decimal point. Here, the author of the book, we are using 2 digits after decimal point. Of course, if you want to be more precise, you use this one. Okay. Here, substitute. What is cosine of 270? What is cosine of 270 degrees? Answer, what's your answer? Cosine of 270 degrees. What's your answer? I will answer now. The answer here equals 0. So, 0 times F1 equals 0. So, the answer, 0. Because cosine 270 degrees is 0. 0 times F1, whatever the value of F1, which is the weight. Whatever the value of F1, which is the weight. Whatever the value, multiply that by 0 is 0. Okay. Plus, what is cosine 0? Cosine 0. I will answer. Equals equals 1. So, 1 times F2 equals F2. I equals F2. Another column. Equals F2. Because this one is cosine of 0 is 1. So, 1. Then, plus, I will just have this one, 0 F1. Anyway, this will end up 0, but I'll just have this one in detail. Then plus F3. F3. sine of theta. Sine of theta. We do not know. It remains sine theta. Because theta is ano? So this one is 0. So what remains is F2. Okay? Plus sine theta. But remember class. I will repeat here. The x component F3x. What quadrant is F3x belong? What quadrant F3x belongs? What quadrant F3x belongs?